You've probably heard of pyridinium chlorochromate, which we actually created in a previous video. This is a selective oxidizing agent for oxidizing alcohols to aldehydes. You may remember it looks a bit like this. Well, not everyone has access to pyridine, so we thought we'd see if it was possible to make a different chlorochromate salt, and instead of using the pyridinium cation we'll use potassium. We're starting out with a large beaker and we're adding 100 ml of water. Okay, here we go. Now we've measured out 115 ml of 36% concentrated hydrochloric acid. Now we add this to the beaker. It's not like sulfuric acid, but the acid dilution in the water does generate some heat, as you can see from the condensation. We've got the beaker on a hot plate and now we're going to gently heat the contents to about 50 degrees C. While that's happening, here's our next reagent. This is 100 grams of potassium dichromate crystal. Note the color carefully, a slightly red-tinted orange. We made potassium dichromate in a previous video, so check this out for details of how to make this from chromium 3 oxide if you want to. The mixture in the beaker is warming up, so we'll add the potassium dichromate to this. A little to begin with, just to check. We're careful here because if the acid is too concentrated it can oxidize to chlorine gas, which we don't want. This looks okay as there's no dark color appearing. So we'll add the rest of the dichromate. Now we're going to continue heating the solution, stirring occasionally and breaking up any lumps until everything has dissolved. The color of the solution becomes a really nice deep orange. Nearly there now. Here we go, everything is in solution. We noticed at this point that the heat was starting to produce some hydrogen chloride vapors in the beaker. So we took the beaker off the heat, covered it with plastic wrap, and then slowly allowed to cool. Chill the mixture for a few hours in order to maximize the crystal. You'll notice that they have a spiky appearance. You might be forgiven for thinking that we'd recovered the load of potassium dichromate, but we haven't. This is potassium chlorochromate. Set up for filtration and filter the crystals. You'll have to shake them about a bit in order to get rid of all the liquid. The literature says that they are hygroscopic, but we didn't notice this just over a short time of a few minutes. Wash with 10 ml of ice-cold water, and then dry thoroughly on the pump. Here's our product. 75 grams of potassium chlorochromate shard-like crystal. The color is slightly lighter than dichromate, more like a fresh squeezed carrot juice orange. Let's do a couple of experiments. Here's a few crystals on a glass dish, and some concentrated sulfuric acid. Very different behavior to dichromate. There's a dark red color like chromium trioxide, a white mist which looks like hydrogen chloride, and an orange gas which looks like chromyl chloride. Pretty but extremely toxic. Okay, now we've got some more crystal in the bottom of a small beaker. Let's add about 1 ml of benzyl, and see how strongly it oxidizes the alcohol. Run away a little hand. To begin with, it looks like not much is happening, but the temperature in there is increasing slowly. The dark color due to the chromium being reduced is slowly forming. and we have liftoff. There's a very strong aroma of formaldehyde in the air as well. This is good stuff, but if we want to use it to oxidize alcohol, we're going to have to be a little bit cautious with it. Let's do an experiment and see if we can use this reagent to selectively oxidize our favorite primary alcohol, benzyl alcohol, into benzaldehyde. We've set up a 250 ml flask with a stir bar, and we've got a cooled water bath set up so that we can regulate the temperature. Here we've measured out 15 grams, which is about 14 ml of benzyl alcohol. Let's get this into the flask. Here we are. Now we can't do the reaction directly because the heat generated will be too great, so we'll need a solvent. We're going to use 20 ml of dichloromethane. This serves two purposes. Firstly, it dilutes the benzyl alcohol and makes the reaction hopefully less vigorous, and secondly, it will boil at a relatively low temperature. If the reaction gets out of control, the DCM will boil, absorbing the energy given off, and give us time to cool the mixture down. The mixture of benzyl alcohol and DCM is slightly milky. We've set this up with a thermometer in the flask so we can see how rapid the reaction is as we add the oxidizing agent. So here it is. This is 26.5 grams of the potassium chlorochromate we prepared. This is a very slight molar excess to the benzyl alcohol. So let's add a little bit and see what happens. There's a definite increase in temperature in the flask, and the color starts to go darker as the chromium is reduced and the alcohol is oxidized. Let's add a bit more. Once again there's a temperature increase, but not out of control. The reaction seems to run quite smoothly at under 30 degrees C, which is quite different to some other oxidizing agents which we've explored in other videos. We continued adding the chlorochromate to the mixture as rapidly as we could whilst keeping the temperature under 30 degrees C. Complete addition took about 15 minutes, and we then allowed the mixture to sit in the water bath and stir for a further 15 minutes. We then removed the water bath and let the mixture stir for another 15 minutes. We switched the stirring right up to make sure everything was mixed and has a chance to react. So here we go, the reaction mixture has a beautiful almond-like benzaldehyde aroma. But we've got to find a way to get this out of the nasty looking mess that we've got. We started off by adding 60 ml of water to the reaction mixture. On mixing well, it looks as though we've got a solid in the flask. So we decided to set up for filtration and see if we could remove this. Filtration was pretty slow, but we got there in the end. We washed the flask with another 50 ml of water and an extra 30 ml of dichloromethane, and used this to wash the solid in the filter. This second filtration is even slower, but we did discover a little trick. By adding 5 ml of 50% sulfuric acid to the mixture in the filter funnel, the precipitate became lighter and the tar component seemed to disappear, making the process much faster. Next step, we transferred our filtrate into a separating funnel. We added about another 20 ml of dichloromethane to help the layers separate. This took a little while as there was still some brown oily material in the mixture. We separated off the bottom DCM layer as best we could. Here we go. This contains our product, so we've got a few options for purifying it, but we're going to use the method of forming a bisulfite adduct. We've got the beaker set up with a stirred bar here and containing about 40 ml of water. Now we're going to add sodium bisulfite to this until we've got a saturated solution. Remember that for this process to work successfully you have to have a saturated solution in excess. Here we go. Nice and saturated. Now we're going to pour in our DCM solution of benzaldehyde. Adduct formation takes a little while to properly complete, so leave the mixture stirring for a good 15 minutes. This is what you should end up with. A nice white crystalline adduct precipitated in the mixture. Let's filter this off. We washed out the beaker with 10 ml of DCM and then used this to wash the precipitate. We then dried thoroughly on the pump for an extended period. Here's the dry bisulfite adduct. 19.5 grams in total. We won't show you how to convert this to pure benzaldehyde because we've done this before in a couple of videos. But this represents a yield of 67%, which is not at all bad. The process is a bit messy, but the oxidizing agent is very easy to prepare and even easier to use in the reaction. An interesting experiment and a good result. Thanks for watching and stay tuned.